Okay. All right, number one, find average value. This is page 17 in your 4345 packet. So we start by setting up our average value theorem. So this one, we don't have a formula to plug in. We're just going to be relying on the regions that we see. Remember, we're only looking at what's between the graph and the x-axis. So I think it's helpful to shade in the region that we're working on. I mean, you may see other shapes, but if it's not between the graph and the x-axis, then it's not part of our graph. And it may not extend from end to end. Pay attention to your bounds, that we don't do the intervals that we involve regions that are not part of the interval. In this case, it is, but just pointing that out. Okay, my a value is -4, my b value is 4, so 4 minus a -4. So we look at the graph to help us find replacements for this definite integral. So if we look, all these are just combinations of triangles and rectangles, or triangles and squares. So I'm going to go through and find the regions, and then keep in mind above the x-axis is positive, below the x-axis is a negative displacement. Okay, so clean up some of these values here. -1/2 and 1/2 will go away. 1 and -1 will go away. So 1/2 plus 1/2 is 1. 1 plus 1 is 2. So my depth integral is 2, but we're looking for the average height, right? So the average height will be somewhere, if we look, somewhere around here, right? You got some negative and positive y values here, so it makes more sense to say 2/8 or 1/4. Visually, it makes sense, right? If you look at 1/4, you can kind of reason out, okay, that looks like it could be, visually, it looks like the average amongst all those y values. We have to make sure we divide or multiply by 1/8. Right. Otherwise, if you think about 2, right, imagine your average value is up here, right? That wouldn't make sense. All your y values are here, so it can't be all the way up here at 2. It's got to be lower than that. All right, number 2, find the average value. Now we're doing the same formula, just now it's a function instead of a graph, and we'll go through power rule instead. Doing average value theorem with calculus, with algebraic methods. Remember, we read from left to right, but we're going to do this from right to left, right? Do the antiderivative first, and then plug in the bounds, and then multiply by 1/2. Both the 4 and the x squared are ready for power rule. Four becomes 4x, x squared becomes x cubed over 3. We evaluate our bounds, 0 and 2. Plug in the upper bound, 8 minus 8/3, right? 2 cubed over 3, 8/3, minus, parentheses, 0 minus 0. To clean this up here, 8 minus 8/3, the same thing as 24/3 minus 8/3, which is 16/3. The 16/3 is not quite our average value, right? I mean, what we found is we found this portion. But we still have to make sure we involve the 1/2, right? So it's 1/2 times 16/3. Which is 8/3. That's our average value. Part B says, find the C value guaranteed by the average value. So all it's saying is, okay, I know what my average height is on the curve. Where is this going to exist? Where is this point going to exist, basically? So we just take our y value, and we're just solving for x, basically. Let me rearrange it so that I can get my x squared to be positive. So I'll add the x squared over to the left side, subtract the 8/3 over. Do some cleanup here. 4/3, the same thing as 12/3. Solve for x. Plus or minus square root of 4/3. And we know we're looking for something between 0 and 2, so we know the negative is not going to make sense. So our C is going to be root 4/3, or you can do some cleanup. Doesn't, yeah, this is fine either. It's fine. Right, number 3, indefinite integral. We always want to consider, can we rely on power rule expansion to do this problem? Can we rely on just power rule and expansion? What's the issue? Why can we not just rely on expansion to resolve this problem? What do you notice about the denominator? Yeah, good. Anytime you have an addition and subtraction inside a radical, we can't do anything with expansion power rule. Our order of operations don't allow us to resolve that. So yeah, we have to go through use substitution. But if we want to use substitution, we want to see a set of parentheses, right? Fourth root of x squared minus 4x. I can raise all that to the 1/4. We can now more easily identify what our u value is. Right, so cross multiply, solve for dx. And now we're ready to make our substitutions back into our problem. Remember, you're only going to replace what you've underlined. Everything else, you want to make sure you keep in your next step. Okay, any questions here? Now, we talked about how if we want to go through your substitution, all of our x's have to cancel out. But these are not quite perfect fit yet. It's close. But is there anything that we can do to make it so that we can get them to look more alike? Yeah, we could. Or we could do what with this? I think this is a little bit easier. If we multiply by 2, then we got to multiply the bottom by 2. I mean, that works, but I want to just consider what can we do here without having to add a bunch of things into our problem. Take out GCF, right? What if we take out GCF of 2? A little bit cleaner. Right now, the x minus 2 are perfectly matched. We can cancel those out. Don't forget about the 2. Let's push that 2 out as a 1/2. Are we ready for power rule? What do you guys think? Yeah, the u has to come up to the top. We're almost there, but remember, power rule is not going to work if the variable is in the denominator. We have to find a way to get that variable to come up to the top. So that means I have to change the exponent to be negative. Now we're ready. Now we can apply power rule. Okay, add 1 to the exponent. So we get negative 1/4 plus 4 over 4, or negative 1/4 plus 1. We'll get 3/4 over 3/4. I'll flip that 3/4 since it's a complex fraction in my denominator. Okay. 4/6 reduces to be 2/3. And then don't forget, if you're doing U substitution, you want to bring back your x variable. All right, number 4. We talked about how absolute value functions, we want to take advantage of geometry to help us rather than going through power rule and doing piecewise functions. I think it's easier to just sketch the graph. It's going to create a V-shaped graph, which we should be able to get 2 triangles to show up, and then we can just find the dimensions of the 2 triangles, add them up, and that's the same thing as going through the algebraic method. Okay, so first start off with thinking about what this absolute value of x plus 3 looks like. Vertex is going to be at -3, 0. Whatever causes my expression inside my radical to be 0 is where my vertex is going to live. Center of my graph. From -3, extend your graph in both directions. To the left, you're going to extend as far left as -5. And then to the right, you're going to extend the 2. So keep in mind, this graph is this equation here. So the strategy here is if I can find the location of the y value at -5, this will also correspond to the height of my triangle. So if I plug -5 into this function, what's -5 plus 3? -2. And then the absolute value of -2 is 2. So 2 also happens to be the height of my triangle. And here, the width of my triangle from -5 to -3, that's a width of 2. All right, plug 2 into the function here to get the location of that y value. 2 plus 3 is 5. My order pair is 2, 5. I'm focusing on that y value, 5 there. So my height is 5. And my width is also 5. Let's add up the areas of these 2 triangles that we see. 1/2 base times height. Okay, 29/2. Any questions, first page? Okay, so first things we ask ourselves is, can we rely on expansion power rule to make our way through? And as soon as we see addition and subtraction inside the radical, we know that we need something. We need something else besides power rule. In this case, it'll be use substitution. Okay, so remember, bounds is the last thing we do, right? We don't touch the bounds until the end of the problem. Okay, make your substitutions, replace the underlying portions with in terms of u, and then keep everything else. All right, x's go away. Don't forget about that -2, which is going to be a -1/2. -1/2 times 2/3, because I'm flipping that 3/2 up. Okay, I still want to involve the bounds, but am I ready at this point to involve the 0 and √7 in for evaluation? What's the issue? Different variables. So on my key, I converted these in terms of u using this formula, but I'm going to bring this back in terms of x and then plug in the 0 and √7. All right, any questions so far? Upper bound first and then lower bound. Now, I do want to point out something that you may have noticed. You see how the bounds, are they in order? But it's okay, because we're doing this algebraically. Whatever answer is going to come out, it'll work itself out. It's just that when you're trying to graph it, having the bounds in order is important, because the number that it represents is misleading. If you see a +2 and things are backwards, then it's really a -2. So if you're trying to graph something, you really want the bounds to be in order. But you don't have to have the bounds in order algebraically. It'll work itself out. Now, if you feel like you really want the bounds to be in order, that's okay. If you want to flip the bounds, you can. If you flip the bounds to get them in order, just make sure you change the sign of the expression before you plug in. Right? So you can't, whatever adjustment you change to the problem, you got to make sure you involve that balancing act. Otherwise, you're changing the problem entirely.
So whenever you have a smaller, like down and bottom, and then No, if you have a small one on top and a big one on the bottom, do you always have to flip it or no?
If you're graphing.
Oh, yeah.
Yeah. Like the even odd, I
Yeah.
would flip this.
So like in this case, should we,
I wouldn't do
like, we
it.
don't even have to touch it, we can just plug it in?
Yes, plug in, yeah. Because if you flip it, then you got to remember to change. You got to change the problem. You got to make that a positive sign. I don't think it's worth the effort. But if you want to do it, you can. Both ways work.
Yeah.
Okay. So what number are we plugging in first? 0. I do want to point out that also, I think sometimes we see 0 and we assume that it's going to wipe everything out. So just be careful about that. Not every time you see 0 means that it's going to wipe everything out. So take the time to actually plug in the 0 and convince yourself what the value is. Don't make that big assumption that every 0 is going to just zero everything out. Okay. In this case, it doesn't. So this is root 7. Root 7 squared is just 7. So I don't have to do a whole lot of cleanup here. I just want to, you don't have to resolve this. Same thing on the AP exam. They will accept numeric values unsimplified. Oh, let me see. Like, oh, sorry. This is negative. I dropped the negative. Thank you. Okay, number 6. Let me adjust number 6 with bounds so that we can kind of extend that problem to what you may see on the test. So number 6, let me rewrite the problem. I'm just going to include bounds for number 6. Sorry, I want to make the lower bound pi over 6 and the upper bound pi over 4. So number 6, if you can include the bounds so we can extend our problem a little bit more. So first thing is recognize that there is no single rule that can handle this. We can't say, oh, there's integral rule for cosine, there's integral rule for sine. I'll just apply both rules and then be done with it. These are being multiplied, so these are connected in ways that we can't just pick and choose different rules just because we see these trig functions. So that means we have to spend the time to rewrite it with a set of parentheses so that we can maybe pick out the potential u value. What could be a good fit for our u value? Cosine x. And if we look ahead, what's the derivative of cosine x? Negative sine x. And the fact that the derivative of cosine shows up elsewhere in the problem is a good sign. Right? That the negative sine x and sine x should cancel out, and we should feel good about moving forward there. Make your substitution. We need the x's to cancel out, and they do. Make sure you keep track of that negative. Everything is nice and clean. We're ready for power rule. 1/3 becomes 4/3, right? We add 1 to the exponent. We have the antiderivative, but we're not ready for the bounds yet. This is in terms of u. These are in terms of x. I'll bring the x back into my answer. Upper bound first. All right, we plugged in our bounds. Can we leave our answer in this form? Keep going, right? We got to at least get these down to fractional values, fractional ratios before we can stop. Okay, cosine of power 4 is √2/2. Cosine of power 6 is √3/2. Now you can stop. Okay, this is where you have to get to before you can stop. Oh, sorry, that's a minus sign. Oh, sorry, plus sign, because the two negatives. Okay, number 7. All right, if we think about expansion power rule, we're stuck, right? Too many terms inside the radical. We see addition, subtraction inside the radical. We can't distribute. We got to rely on u substitution. Okay, what's our u value? 1 minus x. All right, we see some potential hurdles up ahead, right? We know that the x is probably not going to cancel out on its own. We may have to go through another set of substitution to handle that remaining x. Let's see where we get. Okay, any questions up to this step? So I want us to be able to recognize that there is something that's preventing us from moving forward, right? We can't say, okay, x I can push out the front, or x I can do power rule here, power rule here. These are being multiplied. The idea is that if you want to do u substitution, if you want to do power rule, your x has to go away one way or another. We have to find a replacement for x. So the way for us to get that replaced is we have an equation that relates u and x when we went through u substitution. We're going to play with this equation here. So if I solve for x, what's x equal to? 1 minus u. So now this needs to be replaced into here to allow us to eventually get everything in terms of one variable, in terms of u. Now I do want to distribute the parentheses so that I can, or distribute so that I can separate every term and get ready for power rule. I just want to do it once. So I'm going to just rewrite the negative or combine the u and -1 together and then have it in front and just distribute it both at once at the same time. So I like to have my single terms in front and then distribute. Remember, when you're multiplying variables, you're going to be adding exponents. So 1/2 plus 1 is 3/2. Okay. Everything is nice and clean now. Now we can do power rule. 3/2, 3/2. 5/2, 5/2. Bring the fractions up. Okay, are we done? Yeah. So bring back your x. This is only a temporary variable. Bring back your x. Okay, anybody still need number 7? Right, number 8. The complexity of how number 8 looks should remind you, okay, I'm having to do 2 opposing operations on the same function. I see the depth integral, and I see the derivative acting on that integral. So we want to go through a shortcut, and that shortcut is second theorem. Rather than doing a full antiderivative, plugging our bounds, and then turning around and doing the derivative, we're just going to rely on second theorem. Now, this is the adapted variation second theorem with the lower bound. If the lower bound is a variable, or if one of the bounds is if both bounds are variables, they're both going to produce some leftover terms. So first step, upper bound gets inserted into the variable. That's what f of p of x is telling us. Times p prime. So to get the p prime, I have to get the derivative of that root x. Root x, the same thing as x to the 1/2. X to the 1/2, I can do power rule. Minus f of q of x. So now lower bound gets inserted into the function. times lower bounds derivative, -4. Yeah, once you have your expression relatively cleaned up, I'm not going to. I just want to see all the pieces there when you build out your expression, your value. So number 9, we're taking the antiderivative twice, just like how you did on the quiz. So if I want to get to f prime, I'm going to have to take the integral of my starting function, power rule, plus c. We have an order pair at the derivative level that we can use, -1 in for x and 6 in for f prime. I'm just taking my general solution for f prime and updating my c value with 8. This is my halfway, well, this is my part A here. Part B, to get from my f prime up to the f of x level, take the antiderivative again. Power rule. I have an order pair at the function level to plug in, 0 in for x, 14 in for y, for f of x. The practice worksheet that you picked up yesterday has a even and odd function problem. I can go through that. Number 9. So we have two properties. Our strategy is we want to first sketch out the shorter interval. And then after we graph out the shorter interval, we want to flip, or we want to look at what's happening on the other side in terms of, do we want to duplicate it or do we want to do equal but opposite? And then after you have everything you can do with your shorter interval, then you're going to fill in the missing spaces with information from your larger interval. So which interval do we start with? Which one?
0 to 5.
0 to 5, okay. What do you notice that is a little bit off about those properties? Yeah, because this 4 and -3 is a little misleading because it's not really 4 and -3, it's really opposite signs because they're presenting the information backwards here. So let's rewrite this. This is what we really want to be graphing. And this is what we want to be graphing as well. Okay, so we're going to start here, right? This one is now a little bit more straightforward than what we were given before. Okay, so let's sketch our graph from 0 to 5. Okay, before we move on to the other larger interval, what can we say about the other side? Also -4. Yeah, even function. So you're going to make the same, copy the same thing on the other side. Okay, we're ready for the larger interval. Larger interval is going from -8 to 0. So we're going from -8 to 0, but we don't want to be adding anything to this region. We've already finished this portion. So, but we do have a missing gap here. So what I want us to understand is that the -8 to 0 is really adding up regions, and we need the regions to add up to be 3. That's what we really want to do. So what can I put here so that these two will add up to be 3? 7. So this side is 7. What do you know about the other side? 2, 3, also 7. Okay, so now we can add up the region that they're asking us from -5 to 8. -8 plus 7 is -1. Part B. We're trying to find the same region, but now we're saying the function is odd. Start with your shorter interval, just like before. 0 to 5 is -4. So now it's an odd function. What can we say on the other side? +4. We want the region from -8 to 0 to add up to be 3. So we don't want to be changing anything here. We just want to be making an adjustment here. What can we fill on this side? -1. And if this is -1, then this side is a positive 1. Now we're just adding up from -5 to 8. Four minus 4 is 0. 0 plus 1 is 1. Okay, let me know if you have any individual questions.
It's just average out there. Mostly they do it for this and already. It's the one that.
You're just adding up all these regions. So
I didn't get it.
saying, well, first off, you're setting up your 1 over p minus
Yeah.
And then to handle this, we're just adding up all these regions that are the same
Okay,
between the graph and the x-axis.
okay.
Anything below is negative, anything above is positive. So -1/2, +1/2, +1, +1/2, -1/2, -1/2, +1/2, +1/2.
So that would be your F of,
That would be the interval. Okay. So
okay,
here,
that makes sense.
and then multiply that by 1/8.
Yeah, I don't think
I see, guys. All right, see you in class. Bye.
Thank you. Do you have a practice sheet that I can use? But you might tell me that you.
Yeah.
Wait, can you? But I will log this on. Do you know the library? They know we can actually do that. Actually,